Okay, so your warm-up, I asked you to evaluate for when x equals -3, 0, and +3. And let's see here. I'm going to get Abidan. What did you get for when x equals -3 for our first problem? -16. Whoop. There we go. All right. Brennan, how about when x was 0 for that problem? 2. Sarah, how about when x is 3 for that problem? 20. Sweet. Does anyone want to argue any of those? All right, Jayla, how about -3 for the g function, 3x plus 4? -5. Julian, how about when x is 0 for that one? 4. And Connor, how about when x is 3? 13. Good. Yeah, we good? We can evaluate? When we say evaluate when x equals this, you literally replace the x with that value, right? So 6 times -3 plus 2. 6 times 0 plus 2. 6 times 3 plus 2. Okay? Keep that in mind, because when you evaluate a piecewise function, we kind of touched on this earlier, piecewise functions are just pieces of functions, right? So you're going to have multiple functions kind of grouped together. It's not going to be one flowy graph. So when you evaluate, you're going to have a restriction or like a rule you have to follow before you plug in your number, okay? But we know how to evaluate, right? Cool. Let's look at this graph. See how it's not flowy? It has like broken pieces, okay? So work with your partner. At the beginning of the day on Monday, your friend has $300 in her digital wallet. She sends and receives the following electronic payments through Sunday. Okay, so she receives $50. A $50 payment was received on Wednesday. A $150 payment was sent on Thursday. And a $100 payment was received on Saturday. She graphed her balance on the graph shown. Talk to your neighbor. Does the graph represent y as a function of x? Explain. And then part B, according to the graph, what was your friend's balance when x was 2 and when x was 4? After that, do these values match what you expect given the list of payments sent and received? Okay, so work through A and B with your partner. Ready, set, go. Okay, does the graph represent y as a function of x? What do we think? No? Yes? What makes something a function? It has to pass some kind of test. It has to pass the vertical line test. Does this pass the vertical line test? No? Where can I draw a vertical line and it hits this twice? I think it passes. I think it's fine. Yeah. This is a function. The definition of a function is that each input has a unique output, right? Remember doing that? Your x's cannot repeat, but your y's can repeat. Have a good weekend. Okay? So this is yes. This is a function. Yes. It passes the vertical line test. Okay? Each input has a unique output. Okay? So it is a function. Piecewise functions are functions. According to the graph, what is your friend's balance when x equals 2? Thomas? 350? All right. How about when x equals 4, Jayla? I already got Jayla. Just kidding. Arlington. I already called on you. When x equals 4, 250. Okay, so you saw when x was 2, and then here when x is 4, like that. Does this match up what you expected? No? Which one of those do we not agree with completely? The 4? How come?
It's not a steady increase. It's an immediate withdrawal.
Okay, Brianna, what do you think?
I was going to say like they split it up into 2 things instead of giving it to her all on one side.
Okay, yeah, I love all y'all's reasoning. They split up into 2 days instead of showing it all showing up on one day. It showed a steady increase, which really didn't happen. You either have it and then you didn't have it. What did you expect? What should have been there on x equals 4? What amount? Let me re-ask my question. On Friday, she should have, let's think about it. So she started with $300, right? She received $50 on Wednesday. So that brings her up to what? That brings her up to $350. Then she made a payment of $150 on Thursday. That brings her down to what? $200. And then she received money on Saturday, bringing her back to $300. So did anything happen on Friday? No. So what should we expect for her to still have on Friday? She should still have just the $200. Okay. So I would not really agree with the graph that she created. That didn't really show her balance. She should have made more of like a dot plot, to be honest. Which dots are technically piecewise functions. They're itty bitty pieces of functions, but they're there. Okay, so we keep talking about piecewise functions. What are piecewise functions? Also, what is this yellow dot in the middle of my screen? I don't know, but I guess it's just gonna be a part of this with us. Okay. A piecewise function is a function defined by two or more equations. Each piece of the function applies to a different part of its domain. Whoop. Wait for it. There we go. An example is shown below. So see how f of x now has two functions attached to it instead of just one? So my function equals x minus 2 if my x's are less than or equal to 0 that I'm plugging in. And then my function is going to equal 2x plus 1 if x is greater than or equal to 0. Okay, so see how we have two separate pieces? So they don't overlap. One only exists less than 0. The other one only exists when we're greater than 0. What else do you notice about this? They are not connected. Nope. And technically, this came from the book, but technically this guy shouldn't have that equal sign. So notice how one dot is closed and then the other one is open because you can't share the same y value, right? I can't plug in 0 and get 1 and negative 2. That doesn't make sense. If I plug in a number, I should only get one output. So to keep it a function, one of them has to not be equal to, and that's when it's going to be open. What's up? Nope. Nope. The curved equal sign is like approximately, is when you're kind of like guessing on something. So here we just wouldn't have our equal sign at all. It should just be greater than 0. All right. So again, sorry for the yellow dot in the middle. Let's evaluate one of these things. So we're going to evaluate, we're going to graph them, and then we're going to write the function looking at a graph today. Okay, first thing we're going to do is evaluate. Okay, we have rules. We're going to evaluate using 3x minus 1 if I'm evaluating an x value that's less than 2. I'm going to evaluate using x minus 5 if the x value we're using is 2 or bigger. Okay, so part A, x equals 2. Which function are we going to use, Dion? Am I going to use 3x plus 1 or am I going to use x minus 5? And how do you know that? Why did you pick that one? Faith, help them out. Because x is equal to 2. There we go. We're equal to 2. Well, 2 is not less than 2, but would you agree that 2 is greater than or equal to 2? So that's where it falls. So that's the equation I'm going to use. So x minus 5 now becomes 2 minus 5, which is negative 3. So how we write our complete answer is we're going to say f of 2 equals -3, like that. That shows I plugged in 2 into my function, and our output was a -3. All right, how about when x is -1/3? Naya, what do you think? Where's it going to go? 3x plus 1 or x minus 5? How come? Because -1/3 is less than 2. Yeah. So instead of an x right here, now it's going to be -1/3 plus 1. This is what happens when we're plugging in -1/3 into my function. My x gets replaced. What is 3 times -1/3? It is -1. And what is -1 plus 1? 0. So when we plug in -1/3 to my function, I get an output of 0. Okay? This is going to be helpful when we start to graph, because we're going to plug points in, plug x values in to get the outputs, or my y's, to be able to plot points and graph our functions. So we need to know where I'm plugging in my x, so I know which function I'm creating and which graph we're creating. We good? Beautiful. Little something for you to think about. When evaluating a piecewise function, can 2 different inputs have the same output? So can 2 different x's have the same y value? Is that allowed? Yes. Yes, this is allowed. What is not allowed to repeat itself? X's are not allowed to repeat themselves. Okay? If I plug in 2, I can only get one thing out of it. Okay? I cannot repeat my x values, but I'm allowed to repeat y values, right? I'm allowed to repeat like quadratics and absolute values. Didn't both sides have the same y's because they were symmetric on each other? The y's matched, but their x's changed, right? That's okay. So yes. Because it is a function, each input must have exactly one output. But multiple inputs can have the same output. So again, x's cannot repeat, but y's can. So your inputs cannot repeat, but your outputs are allowed to repeat. So when they line up on my graph, like the one above, there should be a close and an open somewhere else. Could I have open on the same vertical line? That's fine, because open means it's not included, right? Can I ever have 2 separate solid dots on a vertical line? No, because that's showing 2 different y values. That's not allowed, okay? Only if they meet up at the same point. If they are joined at the same point, that's when you're allowed to have 2 solid dots. Because no matter where you plug it in, it's going to work for both of them. Does that make sense? Okay. Most of the time, you'll have either one closed, one open, or you'll have 2 open. Ready to graph it? Yay. Hey, I'm being nice. I'm only doing lines. Wait till we get fun. So next unit is our quadratics. So since we haven't done quadratics yet, is why I'm not like making you do them right now. But they're coming. All right, graph f of x equals -x minus 4 if x is less than 0, and then graph x if x is greater than or equal to 0. Describe the domain, range, and end behavior of our function. So when I graph, lots of teachers do this lots of different ways. I make a table. All right, I'm going to make a table. My domain goes from less than 0 to greater than 0. So we know these functions are going to match up when x equals 0, right? That's where one of my functions stops and the next one starts. Okay, so I'm going to have x's. I'm going to have the function negative x minus 4, and we're going to have the function of x. Okay. I want to scan across my graph. I'm going to go as low as -4, -2, 0, 2, 4. If you want to pick different numbers, go for it. I don't care. I'm putting 0 in the middle, though, on purpose, because I know that's where my first function stops and my next function begins. So definitely make sure 0 is on your table. But if you wanted to do 1, 2, 3, go for it. Okay. Now, when I make my table, I'm only going to plug in my value or evaluate for the function that it works for. So when I plug in an x value of -4, which function am I going to plug that into? The top one, right? Because -4 is less than 0. So let's plug that in. -4 minus 4. So what's -4? +4. What's 4 minus 4? 0. All right, let's plug in -2. What is -2? And what is +2 minus 4? -2. All right, what is -0?
0.
What is 0 minus 4? -4. Now I gotta be careful. This one gets our open dot. And I know that because right here, it told me it was not equal to it. So that is where it stops. So I have to show where my line stops, but we're gonna do it with an open point because we're not including it in that graph. Okay. So this is our first function over here. What's up?
So like before we did like the little graph and everything, I just like graphed it. Will that like work every single time?
What are you talking about?
Like I graphed it before.
Yeah, there's lots of ways to do this. Yep, lots of ways. Again, I'm a very visual person. I like to kind of like make charts and stuff. But yeah, if you can look at those equations of lines and just graph the lines, go for it. All right, now 0 is equal to 0, right? So I can jump over to the other side of my table. So if I plug in 0 for x, I get 0. This is going to be nice. This time we're going to get a closed dot. So 0, 0, my origin, gets the closed point. All right, when I plug in 2 for x, it's just 2. When I plug in 4 for x, it is just 4. It is, yep, it's freezing a little bit. Give it a second. And then so you'll have a graph, a line going up 1 over 1. There we go. Okay. 2, 4 on this side. So I see where the first graph starts and the second graph stops. Oh, bonus question. What if these two lines would have met up at the same point? What kind of function would we have made? Ooh, absolute value. Fancy. Could you write any absolute value as a piecewise? Yes. Well, foreshadowing right there. Ooh. I know, fun times. What's nice is it's the same slope, right? One positive, one negative with the same y-intercept. Sometimes, not all the time. Okay, describe the domain, the range, and the end behavior of our entire piecewise function. So remember, domain is referring to our x values, right? So what is the lowest x value on this graph? How far left do we go? All of them, yeah. Isn't it anything less than 0? Yeah? And then my other side, doesn't it go all the way to the right? Yes. And do we have any gaps in the middle? Because that could happen with piecewises. No, because I have a closed point at 0, it includes everything. So a couple places you can look. You can look at your graph. You can look, this is called your domain restrictions right here. So that also gives you your domain. Everything less than 0, 0, and everything bigger than 0, that's all real numbers. Got that fancy R. You can do negative to positive infinity. You can write out all real numbers, however you want to do it. All right, my range. My range is my y values. How low do the y values go? -4. And how high do they go? Forever. Good. So we go from -4 to infinity. Does -4 get a bracket or a parenthesis? Why is it not a bracket this time? Because it's open. So that y value of -4 got an open point. So it's a parenthesis this time.
So the center of the graph is the y value?
Not always. It's just the lowest point. Yeah, we're looking at the lowest point and the highest point. And then the last thing it asks me is for end behavior. So there were 2 pieces, right? We have the left side and we have the right side. Ooh, come on. There we go. So on the left side, is my graph going up or down? Your orange part. Where is it pointing? It's pointing up. So how do I say up in fancy math? To infinity and beyond. And then my right side, the purple, where's that arrow pointing? Also up. So also to infinity and beyond. One day you'll say it with me, and it'll be a fun day. All right. So I'm kind of doing one of each. Your books and your online books, they have like extra practice problems if you need them. Like extra example problems in the book if you need extra example problems. But for time's sake, I'm trying to hit at least one of each. So our example 3 goes now into writing a piecewise function. So now I have the graph. It wants me to write the function. Okay. So what I recognize is what 2 kinds of functions are in this piecewise function. Are they quadratics? Are they cubics? Are they lines? What do I have going on? Is it a point? I have 2 lines, right? I have 2 lines going on. So I know both of them are going to be written as mx plus b. Okay. I'm going to label them A and B to help us out. I'm going to call this guy A. So our line A, I need to know the slope and the y-intercept so I can write the equation for it. So what is my slope for that line A as we move from left to right? How are we getting from point to point? Up 1 over 1. And what is the y-intercept for that line? It is at 3. Good. So what is the equation of that line? X plus 3. All right. Sweet. Now for my line B over here, it is a line. So again, I need slope and I need y-intercept. What is the slope for B? How are we getting from point to point over here? Looks like up 2 over 1. So it's a slope of 2. Oops. And our intercept is -1. So the equation of this line, 2x minus 1. Now, again, this is a nice one where it shows you where they are on the y-axis. Sometimes that's not where they're going to meet up. They might meet somewhere off to the right or to the left. Just continue your slope pattern to see where it would have crossed the y-axis, even if it doesn't show it to you. Okay? What's up? Because you're going up 2 and over 1. I mean, up 1 over 1. We read graphs left to right. We always read graphs from left to right. It's just showing the left side of that line. But the line is moving in a positive direction. That is not a negative line. That is a positive line. I know. That's confusing every year for somebody. We always read graphs from left to right. Okay, so here we go. My function, f of x equals. We have our first line, which is x plus 3. And where is that? That's only existing if my domain is what? What x's are on that first line A? Right here. If my x's are less than 0. Good. How come we're not equal to 0? It's an open dot. Beautiful. Good. All right. Now, line B, we know it is 2x minus 1, but it only exists if what? Greater than or equal to. How do we know this one gets the equal to? Because it was closed. There we go. Good job, guys. It's not always 0. Again, these first couple ones are 0, but they do build, and your homework helps build that skill. What's up?
What if like the x's what if they meet when the x is 1,000? What would you write it as?
Then you would write 1,000. Yep. Yeah, but when you write your piecewise function, your numbers should match up, which you're definitely going to see in our next example. This famous guy is called a what? I'm not going to give it to you. What do you think that graph looks like?
Stairs.
Ooh, stairs or steps. So guess what this is called? A step function. Look at that. Good job, friends. A step function is a piecewise function defined by constant value over each part of its domain. Okay? The graph of a step function consists of a series of line segments. So that's an example of what the graph would look like and an example of what the function would look like. So what's missing? 2, 3, 4, 5, 6. None of them have a what? A variable, right? No one has an x because they're constants. They're flat. That's what makes them a flat step. Okay? This is a whole lot of real life stuff. When you have different movie theater tickets, is it still by age? I haven't been in a while. If you're a certain age, the movie ticket costs a certain price, right? Or if you go to a theme park, okay? If you're this old, you're free. If you're between this age and this age, you're $20. If you're more than this, now you're $50, whatever. Those are all real world step function examples, okay? Where your domain restriction is your age. How old am I? Okay, what does it cost for me to go? Okay, that's a real life step function that you will use if you haven't already. Okay, another example for step functions that you will use is if you're maybe renting something. Okay, don't they usually rent by the hour or something like that? If you rent boats, if you have it for this many hours or whatever. Okay, so in this example, we're renting a karaoke machine for 5 days. The rental company charges $50 for the first day and $25 for each additional day or any portion of a day. Write and graph a step function that represents the relationship between the number of X days and the total cost, which is Y in dollars, renting the karaoke machine. Okay, so the first thing we're going to do is make a table. Okay, so our price changes how often? Every day. Okay, so my first number of days is in between 0 and 1, right? What does it cost for that first day? $50. Am I equal to anything here? We're equal to the 1. So on day 1, you are being charged $50, right? What are you being charged on day 2? $75. Good. So after day 1, but up to day 2, you are now being charged $75. Okay. So we're not equal to 1 anymore because we're past that point. Our price has gone up. See a pattern going on here? So on day 3, so after day 2, up to day 3, we're being charged how much? $100. Good. Think you can finish the table? I bet you can. There we go. Something like that. So you'll see this a lot in our tables where one ends like domain wise, the next one kind of picks up, especially with real world stuff if we're accumulating on it. All right, my functions. This is a step function, right? Yes, each day itself costs a certain amount. There's no increasing or decreasing per minute or whatever. Nope, this is the price for this day, the end. Okay, so my functions are going to be 50, 75, 100, 125, and 150. Okay, and it's going to cost that much if we're in between 0 and 1. So functions are a little bit backwards from your table because tables always go x's and then y's. In your piecewise function, you get the function and then they say if your domain is this. So if your x follows these rules. All right. Okay. So now it's time to graph my steps. Where is my first step going to be?
0.
It's going to be on the 50, right? And it's going to be in between days 0 and 1, right? Is it going to start with an open or close point? It's going to start open and finish closed. Think about it. Doesn't that make sense? If you plug in, I mean, not that we can plug in 0, but doesn't an x of 0 represent 0 days? So if you don't have it, you're not going to be charged for it. Does that make sense? So that's why that first point is open. It depends on the situation. It really does. Stairs, step functions, typically yes. Yes, me too. All right, so my next one between 0 and 2 now has a step at 75. So again, it's open and then closed. And then between 2 and 3, we step up to 100. Then we step up to 125. And then we step up to 150. Like that. It didn't ask you this, but I am. I'm going to ask you for the domain and range. Okay, of this functions. Looking at this piecewise function. If I ask you what is the domain of it, that means we're looking at these, right? What is the lowest x that we go?
0.
Where the lowest is 0 and my highest is what? Is 5, technically, with this representation. So my domain is in between 0 and 5. Does 0 get a parenthesis or a bracket? A parenthesis. What does 5 get? A bracket. Good. All right. How about our range? So you think that goes from 50 to 150 and everything in between? Are there little gaps in step functions? Yeah, because it's only 50. It's not 51. It's not 52. That's not included. Only my values, 50, 75, 100. So we're going to list them. So my range is 50, 75, 100, 125, and 150. Those were our only outputs. So we don't write it in interval notation because it's not a range of values. It is just these values. Those are my only outcomes in this situation. So that's something special that happens in step functions also. All right. Yeah, good times. Great oldies. I'm sorry. I know it's the weekend though. Your 1-6 homework, it is online and it is open until Sunday. Okay? You have 1-6 homework, that you have to do. You have 1-6 homework. It is due by Sunday at midnight.